Hi, my name is Matt Sottile, and I'm going to present a project that I've worked on for a couple of years with a collaborator, Lindsay Arrington, called poco. And poco is an ML testbed for deductive synthesis tool design. So poco is a research sandbox. And it's a research sandbox specifically around looking at design decisions for how you would build a deductive synthesis tool. It's not about synthesis techniques. It's about how you go about building an efficient tool for performing synthesis. And as such, it's a simple language. The tool that we were building that this was born out of was for more complicated languages. And we found that it wasn't easy to try things out in the more complicated tool. So we built a simpler tool so that we could have a sandbox to play in. And we specifically designed it so that we could measure it, we can monitor it, and we can control it. And so a lot of the design decisions that went into this are around that, addressing those concerns. So the starting point for poco was the MinCaml language. MinCaml was created as a teaching language. It was created to make it so you could have a compiler's course where students could work with a simple language, but not too simple of a language. So they could explore building a compiler with a real language, but not get tangled up in all the complexity of a full language. And that's kind of similar to what we wanted. We wanted to be able to have a place to play where it was interesting, but not too interesting to make engineering difficult. And so the starting point was MinCaml. And the first thing we did is we started extending it. So we added a few constructs that OCaml has back into the language, and then added extensions for metaprogramming. So to allow us to express patterns and transformations. And we also had some extensions for expressing strategies for how you apply these. One benefit of this actually was that this meant that we didn't have to build a compiler. Since our tool is working in MinCaml, which is a proper subset of OCaml, when we transform a program, it's also a MinCaml program. And if we strip the extensions out for metaprogramming, we can run it through a compiler and actually see how the result turned out. So the starting point for poco was the same starting point as MinCaml, an algebraic data type for the AST. And immediately you'll see we started to diverge from the MinCaml one. Specifically, if you look carefully at some of these constructors here, you don't see the usual thing you would expect, which is references to the term type itself. So I look at like a binary operator or a unary operator, you see that the children are these things called nods. They're not instances of T. And what that means is these nods are addresses. They're globally unique identifiers. We called them nod, I think is a shortening of node. And the idea there is that when I hit one of these things, if I want to traverse the tree, I have to look over in a map to find the term constructor for the child. And so next to this algebraic data type is a collection of maps that allow us to do this. So we have this nod map, and the nod map is the mapping from these identifiers to the terms themselves. So if I do a traversal, I get a term, I pattern match on it, I find the children, I go over to the map, I look it up, get the nods, get the terms for those, and then repeat the process. The other maps that we maintain are convenience maps. So sometimes we find we want to go backwards through, or we want to go up the AST, not just down. And so we maintain a parent map. The other thing that we want to do is sometimes we have a term constructor we're interested in, like we want to find all the conditionals in the code. And so we want to be able to organize all of the terms so that we can say, okay, given the conditional tag, if, what are all the nods that are if terms? And so we maintain this tag map. For those who've seen it, OBJ Magic also provides us insight into the tags that OCaml uses. We use our own tags. We don't use OBJ Magic, but in Spirit, it's accomplishing a similar thing. So an example of one of these rules. So rules have three parts. They have the pattern to match. That's the thing in the braces at the top. They have the fragment to splice in place of the pattern where it matched. And then the third part is the proof obligation. And this basically says, if I want to do this rewrite, this proof obligation has to be rewritten to true. And so in this case, we're binding these expressions, x, y, body, to metavariables. And so x is an expression that is an assignment to a pair. We're binding the elements of the pair to metavariables. And the transform we want to do is basically to eliminate this second one. We want to get rid of y if we can prove that y and x resolve to the same thing and x is pure. If it's not pure, then we do need to make sure to preserve both because the side effect may be important. And so this is what a rule looks like. Pretty straightforward. And the interesting thing to note, though, is if you look carefully at the metavariables, they're different in some places. So when I have a dollar sign for a meta variable, that means that the meta variable binds to a term value. So it binds to the term itself. If I have an @ sign though, that means that it binds to the nod of the term at that point. And the reason for this is sometimes when I'm doing discharging a proof obligation, I need to not just look at the term structure, but I need to know where it occurred. So I may need to know how to interpret that term in the context of the control flow or in the context of the AST. So the @ sign allows me to access these meta variable bindings by address instead of just their value. Once we've got the rule syntax, one thing we wanted to be able to do was take a program and a collection of rules and find all of the places where any rule matches, so that we can kind of lay out the picture of all the work that could possibly be done at any given step. And so this is accomplished through this term indexing scheme where we compile the set of rules in memory to a try, and then we use the try to do the pattern matching. So in this case, I've got 2 rules, both of which are working with conditionals. And you can see how they get compiled down to this try. So both rule A and B are rooted at if. They're rooted at if constructors. 11 happens to be the tag that we used for if. There are no meta variables bound at the top. That just means we have no rule that's just a meta variable. So A and B both are rooted at if. And then underneath those, we say, okay, well, if each of the subtrees also has a try associated with them. So you can see both the condition and the then clause, both of those bind to meta variables in both rules. So we see like the condition, rule B binds a name P. There's no constraint on what kind of tag goes on, can be bound, and we're binding values. So the dollar signs are being used. The else clause gets interesting. I intentionally put a constant there to show this, but for rule A, it's a meta variable. And so you see for rule A, the else clause just gets bound to this meta variable R. On the other hand, for rule B, we're constrained. It has to be an int constructor. Specifically, it has to be an int constructor for the constant 1. And so that's encoded here. The pretty printer isn't showing you the value that's being bound, but that's kind of baked into this terminal here. And so this is what the rules turn into. So you can imagine a very large rule set turns into one of these kind of big try structures. But the matcher knows how to work with these things and find all matches for a given rule set and a program. So the rule application process is pretty straightforward. When we find a pattern match at some location, I call that @_, we get a set of meta variables that are bound. So the first thing we do is we substitute those into the proof obligation, and then we start transforming the proof obligation. We do that until the proof obligation gets reduced to true. It's worth noting that some of these primitives that are available in the proof obligation may appeal to external tools. So not everything has to occur inside POCO. And we've experimented with using like the OCaml bindings to Z3 so that we can have some of these primitives escape to a proper solver. If we're able to reduce to true, then we can carry on. The proof obligation may itself bind a few meta variables, so we keep those. We put those into the set of meta variables that were bound in the original pattern, and then substitute those into the fragment. Once we've done that, we create a new context where we replace the term that was at _ with the new fragment, and then we update all the supporting data structures. These fact rules that I mentioned, these are a convenience. So what we found is that a lot of times our rules, especially domain-specific rules, may have domain-specific information that you want to learn and accumulate up. And you don't want to necessarily do so in the base language. You could conceivably do this in a type system, but we were like, well, let's see how simple we can make it. And so what a fact rule is, it's expressed the same way as a transform rule. The difference is that when you apply a fact rule, instead of rewriting the tree, we just have a map that basically says for every program point, we have a collection of terms that are associated with that program point. And those are the things that we know are true at that program point. And so we can decorate the AST with those. And when we traverse the AST itself, if we ignore the fact map, you don't even see them. So it's kind of nice in that they're there if we need them, and we can ignore them if we don't want to, if we don't want them. So here's an example of a use of these. So we were doing some experiments with transforming linear algebra codes, specifically one that was using the singular value decomposition. And so we wanted to try and bake some knowledge that we had from linear algebra into the rule system so that we could exploit known theorems to drive transforms. So in this case, just looking at the first rule here, we see that if we encounter a piece of code that says let some triple equal SVD of A, this is the SVD decomposing A into the three constituent matrices, we can learn things about it. So if we see this and we know that A has a certain size, and we know A is a real valued matrix, so somewhere else we were able to make those inferences, we can learn that at program point U, which is the first matrix that comes out, we can associate with U that we know its size. The SVD defines what the size of that matrix is. We also know the SVD tells us that it's a unitary matrix, and we know that it inherits the fact that it's the parent matrix was real that we decomposed, so the component matrices are also going to be real. And we do a similar thing for the middle matrix. We know it's diagonal. And so this is a way of associating knowledge from outside the language and outside the program that comes from our theory into the transform system so that later rules can exploit this. And that turned out to be pretty useful. We use this to implement pseudo inverses so they can kind of figure out that it needed a pseudo inverse instead of a proper matrix inverse in certain cases. So once we've got a set of potential rules to apply, we have a bit of a problem. Which one do we do? And you don't want to exhaustively try them all. It probably will do no harm, but it will just take forever. So we ended up at the same place a lot of rewrite systems do, where we said, okay, we need a strategy and tactic language. We didn't invent anything new here. We just looked around and saw what seemed to be common across a lot of the tools and implemented them within POCO. And so the starting strategy language allows us to group rules, allows us to sequence rules, and it allowed us to have some alternation. So like we could try something, if it fails, try something else. And then we had some form of iteration. We could try it once, n times, or go until a fixed point. And so once we had these, all of these building blocks that allowed us to express rules, find pattern matches, select from the potential pattern matches to prune down the search space, we still had some algorithmic issues to think about. And so specifically, we looked at reducing the work that the tool needs to do. So the first thing we did is we made sure that all the data structures and supporting algorithms were incremental where possible. So for example, when we compute the CFG, if we do a transform, instead of just naively computing the CFG for the program all over again, we incrementally update it. So if you updated just one function and not a bunch of other functions, the CFG for that function is the only thing that gets modified. And so we incrementally update the data structures to minimize the work needed. We also use laziness and memoization where possible. So we pretend as though we've computed everything, but defer the computation sometimes until later. And then when we perform the computation, we remember it, so that the next time around, we don't have to worry about doing it again. And we also try and record the behavior of the rule application. So if we try and apply a rule at a program point and the proof obligation fails, we know that unless the program changes, if we try it again, it's going to fail again. So we remember that so that if the tool happens to try that, to see that potential rule application in the future, it won't even bother unless something's changed. And so that's the last part of this, is that there's a lot of infrastructure in place to make sure that when a splice occurs, so we do change the AST, we update all the maps that implement memoization and this failure tracking so that we don't reuse a result that's no longer valid, and we make attempts to do transforms because that have failed in the past, because maybe we've learned something new and that transform will now be able to proceed. And so we have to look not only at the program point that was changed, but syntactic descendants and ancestors, control flow predecessors and successors, as well as things that are in the same equivalence class. So once we've got this rule set, and so the strategy language says, okay, pick a rule from this collection, because that's what I think you should do next, we still have a problem. We've got like a bunch of rules. So the tool has said, okay, I've got a bunch of potential rules to apply. Which one do I pick? And so what we started to, this is where the experimentation comes in. So we started to say, okay, what if we tried to make it a little bit intelligent? Instead of just relying on what happens to be the ordering that the underlying set provides, we want to maybe associate a priority order with these, where the priority is derived from some observations. And so we start off by defining a simple neighborhood around the terms. So for us, the neighborhood is the term itself, and we just think about what tag that term has, and the parent. So what tag is the parent term? So you can imagine like binary operators that occur in the then clause of if statements. That's one potential neighborhood. And then we run the tool over some examples, and we track for each of these tag combinations, how many successes and failures did we observe? And we want to use that to derive a priority. And so one of the things we do is we say, okay, well, we established that the priority 0, That's the I don't know. It might be useful, might not. We don't have any evidence to say otherwise. We define priorities that are negative to be ones where we have evidence that the tool typically doesn't make progress when it tries it. Positive priorities, typically the tool does make progress. And priorities that are greater than another priority just says that one of them is more likely to yield progress than the other. So given these simple rules, what we do is we take the program, run it on some examples, and then record the behavior of it. And then we post-process those to compute these weights. And so the weights, pretty straightforward. For each of these tag pairs, so parent and or match point and parent tag, we count the number of successes and failures. And so if we saw more successes than failures, we give it a positive weight that is proportional to the number of successes versus the total number of attempts. Similarly, for negative weights, or for places where the rule tends to not succeed, where we saw more failures than successes, we make a negative weight, again, proportional to the number of failures. And if we saw a balance of positive or successes and failures, then it's 0. I mean, you can see here is that if you have like more successes, but only a little bit more, it's going to be close to 0. So it's not going to be off at 1. And so it gives us some of the ordering. And it turns out this does yield some success. So we tried it on the core of a matrix multiply, and we found that without the decision tree, these are the statistics we saw. So 58% of the rules that were attempted succeeded, 15% of the built-ins, so like constant propagation and the usual stuff that's inside a compiler, 15% of those succeeded. And the proofs, we saw that 31 proof obligations went to true, 2 went to false, and 20 were inconclusive. And when we added the decision tree in, interesting thing happened. We saw more rules succeeded. And the critical thing is that the denominators changed. Basically, the decision tree allowed the tool to just not even bother attempting certain transforms that it did otherwise. And it turned out those ones were ones where it was failing. And so we can see that the prover had less inconclusive proofs, which is good. Now, it's worth noting, for this example, we saw success. It did make the tool more efficient. For other examples I tried, it didn't have any effect at all. And then in even other examples, it had a negative effect. And my thinking is this completely removes the ordering. So we remove the time component from this, and we lose the fact that certain rules may be useful early in the transform process and not later, or vice versa. Things might be useful late and not early. And what the decision tree may do is, if by chance, without the decision tree, we happen to be picking certain rules late in the process that are very successful, what we may be finding is that we're prioritizing them, trying them early, and they're failing more often than we'd expect. And so one area of research is how do we make this decision tree try and take into account the ordering, and also possibly take into account more of the neighborhood around the terms. It's an interesting little research area. And again, POCO lets us play with this because it's built for this kind of research. The last thing is just looking at the performance of the tool itself. And so the tool is heavily instrumented so that you can get profiles out. And what we found is that for, I think this is looking at that after a run for the SVD example, we find that the tool is very read heavy on the maps. So it spends most of its time traversing things, looking around and testing the maps. So find and find opt get used all over the place. And it turns out that the trees that we're using are balanced binary trees. And we're paying this lookup time. So the log n lookup time to go and find things in these balanced binary trees is hurting us when you do it a million times. And so what we want is the performance of an array or a hash table where you get a much faster lookup time. But we also want the benefits that these nice, pure, functional balanced binary trees give us. So this is another subject of current research work, is how do we build a data structure that has the performance benefits that we want without giving up the programming benefits of purity, of having a nice functional data structure. And we've been looking at kind of using possibly some kind of transactional data structure to have different phases of representation, depending on if we're in a read heavy or a write heavy section of the code. So to conclude, we found that our term map, the term and map representation is flexible. Compilation to the trie is also useful, and that actually is translated to the parent project. The fact rules provide a nice mechanism for annotating the program, and the incremental data structures also keep things efficient. The code will be released open source soon. It isn't yet, largely because It's not a legal thing. It's just there's some embarrassing bugs in it and some things I want to clean up before I release it. But the plan is to release it into the wild. And so please contact me if you're interested in learning more, or if you want to know when the tool comes out. Otherwise, you can just probably follow me on GitHub, and then you'll see when it becomes a public repository. So thanks for your time, and I'm happy to answer any questions.